Welcome back to the Deep Dive. We're here to take your complex sources, put them through our knowledge extractor, and really give you those fundamental insights, the aha moments that actually matter. Today we're tackling a concept that, honestly, sounds ripped straight from the best kind of science fiction, but it's being taken seriously by climate scientists, astrophysicists. It's fascinating. We're asking you to grapple with, well, the sheer immensity of geological time. To start with this thought experiment. Imagine some advanced species, maybe hundreds of millions of years from now, digging around on Earth. What definitive, really long-lasting proof would they find that we were here? Now, flip that perspective around. If our species just vanished tomorrow, and say 50 million years went by, what proof would a future civilization find that we ever existed? And here's the kicker. What if we weren't the first? What if, millions and millions of years before the first primates were even a thing, there was another advanced, maybe even industrial civilization right here on Earth?
That right there is the heart of this deep dive, the Silurian Hypothesis. It's this really elegant thought experiment. It was formally proposed by astrophysicist Adam Frank and climate scientist Gavin Schmidt in a paper back in 2018. And it's really important to understand what they were trying to do. They weren't actually trying to prove that, dinosaurs built skyscrapers or anything like that. In fact, they explicitly say they strongly doubt any kind of pre-human civilization existed.
Right, they're skeptical themselves.
Exactly. Their real goal was sort of twofold. First, they wanted to figure out what the definitive geological fingerprint of an industrial society actually is. And second, use that definition to help with two really big scientific endeavors.
Oh, okay. So it's like a tool. If we can figure out what a, say, 50 million-year-old technological footprint looks like, then we're also defining how long our own impact, the Anthropocene, the age of humans, might last geologically.
Precisely. And it also radically improves how we might search for alien life, astrobiology. If we know what kind of subtle geological traces to look for here, maybe we can look for similar things on other planets.
That makes sense. Sort of refining the search parameters.
Exactly. And just quickly, to clear up any confusion about the name, in a fun little nod to pop culture.
Right, the Doctor Who connection.
Yes. It comes from the reptilian humanoids in the BBC series Doctor Who, the Silurians. They supposedly had this advanced civilization way before humans. It's not named after the actual geological Silurian period. That was much, much earlier, like 440 million years ago.
Okay, good clarification.
Yeah.
So let's dig into this. Frank and Schmidt basically invented, the opposite of SETI, the search for extraterrestrial intelligence, instead of telescopes looking out.
We're using geology to look down into Earth's own deep past for these sort of ancient ghost traces.
But if even the authors are skeptical, and common sense says finding, a dinosaur cell phone is ridiculous, why is this search so incredibly difficult? What makes finding evidence so hard?
The difficulty, well, it really boils down almost entirely to the immense, almost unimaginable scope of geological time. And to really get a handle on the challenge, we need to sort of establish the timeline first. The authors kind of benchmark this by looking at when there was enough available energy, enough fuel to power an industrial society like ours. They point out that there's been sufficient fossil carbon, coal, oil available since roughly the Carboniferous period.
And that was
around 350 million years ago.
Million years. Okay, let's just pause on that number. Modern humans, Homo sapiens, we've only been around for maybe 300,000 years, right?
About that, yes.
So if you imagine that entire 350 million years as just one single calendar year, our entire human history is what, like the last 10 minutes of New Year's Eve?
Something like that, yeah. And our industrial era, the time we've been having this massive global impact, that's less than the final second before midnight. We are, geologically speaking, just a flash in the pan.
A cosmic blink. Okay, so any civilization that might have existed in that enormous stretch of time between the Carboniferous and us, they're up against this relentless geological erasure. You called it a geological buzzsaw.
That's a good way to put it. And this leads us straight to what we can call the fossilization problem. People immediately think, oh, maybe we'll find a pre-human artifact, a tool, a piece of a building. But in this context, that's almost pure fantasy.
Why? Stuff gets fossilized all the time, doesn't it? Dinosaur bones, shells.
Yes, but fossilization mainly happens to organic material, bones, teeth, wood, shells. And even then, it only happens under very specific, pretty rare conditions, like rapid burial in sediment, low oxygen to prevent decay. You need the right chemistry.
Yeah.
Steel, concrete, ceramics, plastics, the stuff we build with. They generally don't mineralize in the same way. They tend to oxidize, rust, crumble, dissolve chemically over geological timescales. They just don't play by the same fossilization rules.
But what if they had, super advanced materials, maybe something incredibly durable we haven't even invented?
Even then, even if you had some miracle material, the Earth itself is the ultimate eraser, and that's where erosion and plate tectonics come in.
Right. The planet is constantly changing its surface.
Constantly. We have wind, water, ice, all relentlessly grinding down surface structures into tiny sediments, sand, silt, clay. Then those sediments get buried under more sediments, compressed, heated.
And sometimes they get pulled down deep into the Earth.
Exactly. That's subduction. It's where one tectonic plate slides underneath another, carrying surface rocks deep down into the Earth's mantle. Once that material gets down there, it's subjected to incredible heat and pressure. It melts, it gets mixed up, chemically altered, what we call metamorphic alteration.
So it's basically reset. Any structure, any complex chemical signature from a civilization is just gone, wiped clean.
Wiped clean. That material might eventually come back to the surface, maybe millions of years later, as volcanic rock or something similar, but it's completely reformed. The original information is lost.
So anything built on the surface probably gets ground down, and anything buried deep gets melted. Is that why the sources stress that most of the exposed rock we see on Earth's surface today is relatively young, from the Quaternary period?
That's a huge part of it, yes. The Quaternary only started about 2.5 million years ago. Most of the stuff older than that is either buried really, really deep under kilometers of younger rock and sediment, or it's already been through that tectonic recycling process.
2.5 million years. That's still a long time, but compared to 350 million.
It's nothing. So finding a physical artifact from, say, 50 million years ago means finding rock strata from that specific time that has somehow avoided being deeply buried, intensely heated, squeezed, or chemically altered for all those millions of years. And it has to be accessible near the surface today.
It sounds like looking for a single specific grain of sand on, all the beaches in the world, but knowing that 99.9% of the beaches have already been melted and turned into new rock.
That's a pretty good analogy, actually. The odds of finding direct physical evidence are just vanishingly small. So the real value of the Silurian hypothesis isn't really about finding a fossilized spaceship.
It's about forcing us to think differently.
Exactly. It forces scientists to pivot. If we can't find the tools, we have to look for the impact. We have to figure out what the large-scale, persistent geological signature of a technological society looks like over these immense timescales.
Okay, so stop thinking about finding a specific object and start thinking about, the planet's metabolism going haywire because of a civilization's activity.
That's the direction, looking for the indirect fingerprints.
Right, so if direct artifacts are pretty much off the table, the whole search hinges on finding these indirect clues, these sort of global, persistent chemical signals or sedimentary layers. The smoking guns buried in the rock record. We're basically looking for the planet-scale waste products of a civilization. And the most obvious, the biggest impact a technological society has is probably on its climate and atmosphere, right?
So are we looking for signs of super rapid climate change, like way back then?
That's definitely one of the primary targets, yes. The sources suggest looking for evidence of massive, very rapid, but maybe geologically short-lived spikes in global temperature and big disruptions in the carbon cycle, all embedded in the rock strata.
Okay, but the Earth's climate has changed dramatically throughout its history, naturally, hasn't it? Ice ages, warm periods. How do you tell the difference between a natural climate shift and one caused by, dinosaur factories?
That is the absolutely critical challenge. How do you distinguish a technological shock from a purely natural event? The authors use a specific example as a comparison point, the Paleocene-Eocene thermal maximum, or PTM. The PTM, that was around 55 million years ago. I remember reading about that, a big natural global warming event.
Exactly. About 55 million years ago, global temperature shot up dramatically. It was associated with huge releases of carbon into the atmosphere and oceans. So on the surface, it looks like the kind of signal we might be searching for.
So if we find a similar spike from, say, 100 million years ago, how do we know if it was another PTM-like natural event or something else? What's the telltale sign of technology?
It really comes down to two main things: the rate of change and the specific isotopic signature of the carbon that was released.
The speed.
Yes, the speed. The PTM, while rapid in geological terms, likely unfolded over thousands, maybe tens of thousands of years. Human industrial civilization, on the other hand, has pumped a comparable amount of carbon into the atmosphere in just a couple of centuries.
Ah, okay, so centuries versus millennia. That's a huge difference in pace.
A massive difference. And that difference in rate should leave a distinct signature in the sedimentary layers. If future geologists drilled a core sample, they could analyze the layers very finely. A natural event like the PTM might show the carbon isotope shift spread out over, say, several centimeters or even meters of sediment representing thousands of years.
Whereas a technological release
Would be incredibly abrupt. It might appear as an almost instantaneous spike, compressed into a millimeter-thin layer or maybe even less. That extreme sharpness, that concentration in time, would strongly suggest a very fast, non-natural trigger.
like flipping a switch, geologically speaking. Okay, rate is one thing. What about other chemical clues in the sediments? You mentioned anomalies.
Right. Industrial activity doesn't just release carbon dioxide. It potentially leaves behind all sorts of other weird chemical traces, things that just don't occur naturally in those combinations or concentrations, buried deep underground or on the ocean floor.
Like what specifically? What kind of unnatural chemistry are we talking about?
Well, think about large-scale agriculture. Any big civilization needs to feed itself, and that often means manipulating the environment. The sources mention looking for evidence related to artificial fertilizers.
How would fertilizer leave a trace millions of years later?
It's about disrupting natural cycles, particularly the nitrogen cycle. Making artificial fertilizer, like ammonia using the Haber-Bosch process, requires pulling nitrogen gas out of the atmosphere and fixing it industrially. This process can alter the natural ratio of nitrogen isotopes N14 and N15.
Isotopes again. So you'd look for a layer of sediment where the nitrogen isotope ratio is suddenly wrong, skewed compared to the layers above and below.
Exactly. If you find a distinct layer with an unnatural N15 abundance, that points towards massive industrial-scale manipulation of the nitrogen cycle, most likely for agriculture. It's a subtle but potentially very powerful fingerprint connecting food production to geology.
That's pretty cool, connecting farming to rock layers. What about energy, besides fossil fuels?
If a civilization was really advanced, they might have tapped into other energy sources. The sources speculate about things like large-scale geothermal energy. Imagine drilling deep and extracting heat from the Earth's crust on a massive scale.
How will that leave a trace?
It could potentially alter the chemistry of deep underground water reservoirs, or even leave subtle traces in igneous rocks formed later. You might look for unusual concentrations or ratios of elements associated with deep geothermal fluids, things like silicon, maybe specific trace metals, or sulfur isotopes suggesting a large-scale artificial hydrothermal system was active.
So evidence of messing with the Earth's internal plumbing on a planetary scale. Okay, now let's talk about waste. Things built to last, or at least things that refuse to disappear. Plastics are the obvious modern example. How long could they possibly last?
The persistence of waste is a really key indicator. While natural organic materials decay and even metals corrode, many materials engineered by industrial societies are designed not to break down easily. Plastics are a prime case.
But they do break down eventually, don't they, into microplastic?
They break down, but they don't necessarily break apart chemically, not fully. They become smaller and smaller particles, microplastics, nanoplastics, but the synthetic polymers themselves are incredibly persistent. They get incorporated into sediments, soil, even rock.
So what would future geologists actually find?
Geologists are already talking about technofossils. The sources suggest that future researchers might find a distinct sedimentary layer containing a high concentration of these microscopic plastic fragments. Perhaps they'd even find fused conglomerates of melted plastic mixed with sand and rock, something people have started calling plastiglomerate.
Plastiglomerate.
Right.
A rock made partly of plastic.
Essentially, yes. Finding a widespread layer like that, full of complex synthetic polymers that simply don't exist in nature, would be an absolutely unmistakable marker of an industrial civilization that produced plastics on a massive scale. A plastic horizon in the rock record.
Wow. Okay, so we have climate spikes, weird nitrogen ratios, maybe geothermal signatures, plastic horizons. These are getting pretty specific. But even plastics might chemically degrade or get buried too deep over, say, hundreds of millions of years. This brings us to the really durable stuff, right? The potentially ultimate signature.
Yes. This is where we move from looking at the environmental consequences of technology, to looking for the direct chemical fingerprint of the technology itself, specifically nuclear technology. We're talking about isotopes again, but ones that nature simply doesn't create under normal Earth conditions.
Right. This seems like the most powerful evidence. Not just circumstantial stuff like climate change or plastics, which might have weird natural explanations, but actual atomic signatures that could only be made by advanced technology. So, what are these definitive isotopes?
The most compelling evidence, the sort of holy grail, would be finding highly specific isotopes, particularly heavy ones, that have no significant natural source on Earth today. Nature makes elements and isotopes in stars, supernovae, and through radioactive decay chains over billions of years. Industrial civilizations can make unique ones much faster, using things like nuclear reactors or particle accelerators.
Okay, so what's the specific element? What's the golden ticket isotope that, if found in an ancient rock layer, basically proves a technologically advanced civilization was there?
The ultimate hypothetical find, according to Frank and Schmidt, is plutonium-244.
Plutonium-244. Why that specific one?
There are a couple of really critical reasons. First, its half-life. Pu-244 has a half-life of about 80 million years. Now, that's relatively short compared to the age of the Earth, but it's long enough.
Long enough that if a civilization existed, say, 50 or 60 million years ago and produced it,
there's a chance some of it, or at least its distinct decay products, could still be detectable today. It hasn't completely vanished from the record yet, potentially.
Okay, so the timing works out. What's the second, maybe more important reason?
The second reason is the clincher. There is essentially no naturally occurring plutonium-244 left on Earth. Any Pu-244 that was created when the solar system formed billions of years ago has long since decayed away because of that 80 million year half-life. The only way Pu-244 arrives naturally now is in absolutely minuscule trace amounts from things like supernova explosions reaching Earth.
So finding any significant concentration of Pu-244 in a specific geological layer from, say, the Eocene epoch
could basically only mean one thing. A technologically advanced civilization was present and was actively creating transuranic elements through nuclear processes. It's about as close to a smoking gun as you can get in geology.
But wait, if the half-life is 80 million years and we're looking back 50 or 100 million years, wouldn't most of the original Pu-244 be gone anyway? How would we even detect it?
That's a fair point. We might not find detectable amounts of the original Pu-244 isotope itself, especially if the civilization wasn't around for very long or didn't produce vast quantities. This is where the really clever part of isotope analysis comes in, looking for the decay products.
The daughter nucleus,
yeah,
what it turns into as it decays.
Exactly. Pu-244 decays primarily through alpha decay, kicking off a long-chain reaction that eventually leads to stable isotopes, particularly of elements like uranium and thorium. The key is that this decay path produces a very specific, unnatural ratio of these daughter isotopes in a localized area.
So you wouldn't necessarily look for the plutonium itself, but for a weird, localized pocket of, say, unusual thorium isotopes that shouldn't exist in that specific combination naturally.
Precisely. If you find sediments highly enriched in these specific decay products with isotopic ratios that don't match any known natural process, that serves as extremely strong evidence that an artificial parent element like Pu-244 used to be there. It's like finding the specific type of ash left by a unique kind of fire, even long after the fire is out.
That's incredibly clever. Forensic geochemistry. We actually know this kind of analysis works over truly immense timescales because of that amazing natural phenomenon in Africa, right?
Yeah.
The Oklo reactors.
Oh, yes, the Oklo analogy. It's fundamental to the Silurian hypothesis because it proves that these kinds of isotopic signatures, even from nuclear processes, can be preserved and deciphered billions of years later.
Okay, let's quickly recap Oklo and Gabon because it's just such a wild story. What exactly happened there, like 2 billion years ago?
Right, around 2 billion years BP, before present conditions at Oklo were just right for natural nuclear fission to occur. Back then, the natural concentration of the fissile isotope uranium-235, U-235, was much higher than it is today, maybe around 3%.
Which is similar to the enrichment level needed in many modern nuclear reactors.
Exactly. And critically, groundwater seeped into these rich uranium deposits. The water acted as a neutron moderator, slowing down neutrons released by natural uranium decay. When the concentration of U-235 and the water conditions were right, it reached critical mass, and spontaneous, self-sustaining nuclear fission chain reactions started.
Nature built its own nuclear reactors.
Several of them, it
Yeah.
seems. And they apparently operated intermittently for hundreds of thousands of years. They'd run until the heat boiled away the groundwater moderator, then shut down, cool off, let water seep back in, and start up again. A natural pulsing reactor.
Mind-blowing. But the key question is, how did scientists figure this out 2 billion years later? All the really exotic, short-lived fission products would have been long gone by then.
They used isotopic analysis, focusing on two main things. First, they looked at the fuel itself. In the Oklo ore samples, they found that the concentration of uranium-235 was significantly depleted. It was lower than the standard natural abundance found everywhere else on Earth.
Because it had been burned up as fuel in the natural reactors.
Precisely. That was the first big clue. But the definitive proof came from analyzing the fission products, the isotopic remnants, the nuclear ash. They looked at elements like neodymium and ruthenium.
Okay.
These elements have several stable isotopes. When they're formed naturally through geological processes or stellar nucleosynthesis, they occur in very specific, predictable ratios. However, when they are produced as byproducts of nuclear fission, the ratios of their isotopes are completely different, skewed in a very characteristic way that only fission can produce.
So the scientists found neodymium at Oklo that had an isotopic fingerprint-matching fission, not nature.
Exactly that. They found isotope ratios for neodymium, ruthenium, and other elements that could only have been created through sustained nuclear fission reactions. That isotopic signature was preserved for 2 billion years.
Wow. So Oklo provides undeniable proof.
Yeah.
If nature's relatively gentle fission process leaves a clear, readable signature for 2 billion years, then the potentially much more intense, widespread, and chemically unique processes of an advanced industrial civilization
Should absolutely leave a detectable chemical or isotopic signature across mere tens or hundreds of millions of years. The physical structures might vanish, but the chemical ghosts, especially the isotopic ones, are likely much more resilient.
The rocks remember, even if it's just at the atomic level.
So you take this realization that finding direct physical evidence on Earth is incredibly hard, maybe impossible, but that these subtle chemical and isotopic traces might persist, and it naturally leads Frankenschmidt to think about, well, looking elsewhere.
Right. This brings the astrobiology connection back in. If we're struggling to find traces of a hypothetical ancient civilization here, partly because Earth is so active geologically, maybe the evidence isn't on Earth anymore.
Or at least maybe better evidence is off Earth. The sources specifically speculate that finding proof might actually be easier on other celestial bodies like the Moon or Mars.
Why would the Moon or Mars be better places to look for traces of an ancient Earth civilization than Earth itself? That seems counterintuitive.
It comes down to preservation. Earth is incredibly dynamic geologically. We've talked about the constant erosion, the plate tectonics, the subduction, the volcanism, the weather. All these processes work together to destroy or deeply bury ancient surfaces and any artifacts on them.
Okay, Earth is messy.
Very messy, geologically speaking. The Moon, on the other hand, is almost the complete opposite. It's essentially geologically dead. It has no significant atmosphere, so no wind or water erosion to speak of. It has no plate tectonics.
So something landed there.
It just sits there. It might get covered by a fine layer of dust from micrometeorite impacts over millions of years, but it doesn't get ground down or subducted. If a pre-human civilization from Earth was spacefaring, even in a limited way, maybe they sent probes, maybe they established a small base, maybe even just crashed something, there the wreckage or the artifacts could potentially remain on or near the lunar surface, relatively undisturbed, for literally billions of years.
It's like a planetary museum, an almost perfect time capsule just floating next door.
Exactly. The very things that make Earth habitable, its dynamic geology and atmosphere, also make it terrible at preserving its own deep history. The Moon's desolation is its archival strength.
And Mars. It's somewhere in between geologically.
Mars is less active than Earth, but more active than the Moon. It definitely has wind erosion, dust storms, evidence of ancient water flows, maybe some minor volcanic activity in the past. But crucially, it doesn't appear to have active plate tectonics like Earth does. There's no large-scale surface recycling via subduction.
So evidence might get buried on Mars, but not necessarily destroyed or melted.
Correct. If a civilization, maybe 100 million years ago, left behind structures, mining operations, maybe even waste dumps on Mars, those sites would likely get buried over millions of years by dust and sand, the slow Martian erosion. But they wouldn't be subjected to the kind of intense heat, pressure, and chemical alteration they'd face deep within Earth. They might be preserved under the Martian regolith, waiting for some future rover or astronaut to stumble upon them.
So Searching on Mars or the Moon potentially flips the script. Instead of looking for subtle, global chemical traces buried deep in Earth's rock.
You could be looking for actual, discrete, physical artifacts or structures, even if they're broken or buried. Finding even one unambiguous piece of manufactured material, one straight line where nature wouldn't make one, on the Moon or Mars, that would be monumental. It would prove either that an advanced pre-human civilization existed on Earth and went to space, or that extraterrestrial life visited our solar system long ago.
Either way, a game changer.
Absolutely. And it ties back into the broader search for alien life. Astrobiologists often focus on biosignatures, signs of life itself, like certain gases in an exoplanet's atmosphere. The Silurian Hypothesis highlights the importance of also looking for technosignature signs of technology. And paradoxically, those technosignatures might be easier to spot off-world on a quieter neighbor like the Moon or Mars than on the potentially noisy home planet itself.
It's a fascinating thought that maybe the longest-lasting, clearest evidence of a civilization isn't a pyramid or a fossil, but maybe just a discarded tool or a spent rocket stage sitting silently on the Moon for 1 billion years. The act of reaching space might be the most permanent mark a species leaves. Okay, before we wrap this up, we definitely need to touch on the pop culture side again, because as you said, the name itself comes from fiction, and it shows how these ideas sometimes bubble up in stories long before scientists formalize them. We mentioned the Silurians from Doctor Who, first appearing way back in 1970. Reptilian humanoids supposedly ruling Earth millions of years before us who went into hibernation to avoid a catastrophe.
Right, and what's interesting, as Frank and Schmidt noted in their paper, is that while it's a staple of sci-fi, they were actually kind of surprised how rarely the specific hypothesis, looking for geological traces of a past industrial civilization on Earth, had been explored rigorously in scientific literature before their work.
Yeah, it seems like such a compelling question. Why wasn't it studied more? Maybe just the sheer scale of geological time makes it feel too speculative.
That could be part of it. It's hard to get funding to look for something you strongly suspect isn't there. But the idea has appeared in other science fiction beyond Doctor Who.
They cited one novel specifically, didn't they?
Yes. James P. Hogan's 1977 novel, Inherit the Stars. It apparently features a similar premise where evidence of a pre-human spacefaring race is discovered elsewhere in the solar system, forcing a rethink of Earth's history. A classic take on the idea.
And sometimes the fictional takes get really deep into the type of evidence, not just finding artifacts.
Oh, absolutely. Larry Niven's 1980 short story, The Green Marauder, is a fantastic example of thinking about deep-time environmental conflicts.
Right, that's the one with the ancient alien recounting a plea for help from Earth's dominant life forms about 700 million years ago. What was their crisis?
Their crisis wasn't asteroids or invaders, it was biochemistry. The dominant civilization back then was anaerobic. They didn't use oxygen. Their existential threat was the rise of chlorophyll, the explosion of photosynthesis across the planet.
So, the Great Oxidation Event, from their perspective, was pollution. The rise of plants was poisoning their world with oxygen.
Exactly. It's a brilliant illustration that a civilization's major impact, its signature, might not be steel and concrete, but its interaction with the planet's fundamental chemistry. Just like our release of carbon dioxide is fundamentally altering the atmosphere today, their struggle was against the rise of oxygen. It's about metabolic footprints.
That really drives home the point about looking for chemical and atmospheric signals. And sticking with popular franchises, Star Trek also dipped into this, right?
Yes, the Voyager episode Distant Origin from 1997 is almost a perfect fictional echo of the Silurian Hypothesis's challenges.
That's the one with the Voth, the spacefaring species who are descended from dinosaurs that left Earth millions of years ago.
That's the one. And when the human crew asks the Voth scientists why there's no trace left of their advanced ancestors on Earth, the Voth explain their theory. Their ancestors likely evolved on an isolated continent that was later destroyed or drastically altered by cataclysms.
And any cities or artifacts?
Would have been obliterated, buried under oceans, ground up by erosion, or recycled by tectonic activity over the intervening millions of years. It perfectly captures the great erasure problem we discussed earlier.
So even in fiction, the biggest obstacle to finding ancient civilizations on Earth is usually Earth itself, its relentless geological processes. The need to look for subtle, indirect chemical ghosts seems almost inevitable, whether in science or sci-fi.
It really reinforces the core idea. The planet's dynamism is both life-giving and history erasing. #outro.
So after this deep dive into searching for geological ghosts, What's the main takeaway for you, the listener? What does this all really mean?
I think the fundamental point is that the Silurian hypothesis, while framed as looking for the past, is actually an incredibly powerful tool for understanding the present and the future. It's about understanding the Anthropocene.
How so?
By forcing us to define with real scientific rigor what the long-lasting geological signature of an industrial civilization is, we are simultaneously defining the signature that we are creating right now.
Ah, right. All the things we talked about. Looking for the rapid carbon spikes, the weird isotope ratios like 2,244, the nitrogen cycle disruptions, the plastic layers, the potential geothermal traces. Those aren't just hypothetical markers of some past civilization.
They are literally the markers we are actively embedding in the geological record at this very moment. We are creating that sharp carbon spike. We are making technofossils. We are altering global chemical cycles. We are producing isotopes like plutonium-244. We are, in effect, creating the very Silurian evidence that Frank and Schmidt proposed looking for.
So studying this hypothetical past helps us understand the true permanence or lack thereof of our own impact.
Exactly. It gives us profound perspective. Our entire civilization, with all its complexity and technology, has existed for such a tiny, tiny fraction of Earth's history. Yet in that geological blink of an eye, we've managed to create a disturbance that might be detectable in some form for potentially hundreds of millions of years. It highlights both our power and our transience.
The sheer difficulty of finding evidence from, say, 55 million years ago really underscores how vast geological time is and how fleeting even our most impressive structures will likely be on that scale. But our chemical waste, that might be another story.
Our waste, our chemical alterations, our isotopic signatures, those might be our longest-lasting legacy written into the rock itself.
Which leaves us with a final provocative thought for you to ponder. We know that even these powerful markers, plastics, Pu-244, chemical anomalies, will eventually degrade, decay, dilute, or get recycled deep into the Earth's mantle over immense timescales. Given the planet's relentless capacity for erasure, what single trace from our current human era, perhaps something very localized but incredibly resistant, will be the absolute last thing to disappear from the geological record? Could it be the altered rock deep within a geothermal well? Maybe the vitrified, stable core of a deep geological nuclear waste repository? Or perhaps something surprisingly small and simple, like a synthetic diamond created in a lab today, buried by chance, resisting heat and pressure for potentially billions of years? What will be the final fading echo of our entire, complex, technologically advanced, yet ultimately fleeting civilization? We'll leave you with that thought.